the columns here. Any place on here.
So just listen carefully, and you might have to walk through it. You'll hear it get loud and quiet, loud and quiet. Find a spot where it gets really quiet or all this goes away.
This side of the column.
No.
Find a spot where you can almost not hear it. When you find a spot, stay there. It's got to be different, though. Only one person per spot. We can barely hear it.
Found a spot where it gets considerably quieter. Okay, let's see if we can put some meaning to this here.
Don't move.
So don't move, stay where you are.
Okay.
So let's figure out the wavelength of this frequency. The speed of sound is approximately 1,130 feet per second, or 344 meters per second. If I divide that by the frequency of 200 hertz, I get about 5.5 feet. So the wavelength of 200 hertz is going to be, around 5 or 6 feet, which means if you find a spot in the air where these two waves are canceling out, the next spot where they cancel out should be 6-ish feet away. Okay? So what's interesting is you look at where everybody's standing, like here over here. We have people that are standing approximately 6 feet apart from each other. Okay? See? 6-ish feet apart in some cases. Because you're all finding spots where it's canceled out. The next place is going to be 6 feet away because of the wavelength of that frequency. What's happening here is this loudspeaker is generating sound, and this loudspeaker is generating the same sound. And for you, this loudspeaker is closer than this one, right? So this one will hit you later. And when it hits you later, that's an offset in time, and an offset in time creates a phase difference between the two waves when they hit you. If they arrive 180 degrees or some multiple thereof out of phase, and guess what? You get a cancellation. Everybody got that? Okay, you can have a seat.
Don't forget the answers.
Oh yeah. 2 answers to every question. And so whenever I ask, hey, why is this happening? Your options are, it depends. Okay. Answers number 2 is, it's the phase. Okay, so you got 2 shots at it. So take a guess. All right, so that's interesting, right? That was physically happening. You could hear that. You could hear when it got quieter as a result of the cancellation. However, we don't usually hear these kinds of sounds in real life, right? We don't listen to pure sine waves very often because they're not particularly pleasant. And honestly, they don't really exist often. But we listen to more complex sounds like music. Music is a complex sound. It has lots of frequencies. So let's take a look at what this means at when you have multiple frequencies happening. So just for purposes of demonstration, I'm going to use a sort of a random noise source called pink noise. Pink noise is something that basically has equal energy per octave band of frequencies. Okay? It sounds to us as though all frequencies are equal. White noise is all frequencies equal. I'm going to delay it. So I've got 2 instances of this sound. Turn one of them off, one of the last ones off. So I've got 2 instances of the pink noise. I'm going to delay one of them in time. And we know that from hearing it, the changes in time okay, so I offset it by 19 samples. All right, well you can hear something happen, right? But you can see it here on the frequency response scale. Okay, this is our range of frequencies, 100 hertz to 20,000 hertz, and then we have magnitude. You can see that some frequencies are getting quite a bit quieter, right? In some cases, completely canceling out. Other frequencies are getting a little bit louder. Why? Why is this happening? Who said the phase? The phase, very good. It's the phase. You take care of me here. Okay, so it's the phase. And what's interesting about this is that same offset in time results in a phase difference that changes per frequency. So for some frequencies, that offset in time is a 180-degree phase relationship. For other frequencies, it's a 360-degree phase relationship. For other frequencies, it's somewhere in the middle. But it's different per frequency. And the frequencies that have a 180-degree phase relationship cancel out. The ones that have a 360-degree phase relationship, they reinforce and get louder.